Today we're looking at stationary points. Now a stationary point has a gradient of 0, so it's a part on the curve that's actually horizontal. Now there's 4 possibilities for the shape of the curve on either side. Either it's a high point and it's like the top of a hill, or it's the low point, sort of at the bottom of a gully, or it's going from low to high, or from high to low. So these are the 4 shapes that we're looking for, so that when we find a flat spot on a curve, or a point that has gradient 0, we can identify what type of flat spot it is. Now make sure you understand that when we're finding a part of the curve that has a gradient of 0, the curve right at that point, let's call that point x equals a, the curve has a gradient of 0, but also the tangent to the curve would have a gradient 0. So if we draw a tangent on any of these, we can see that that tangent would indeed have a gradient 0 and be horizontal or flat. Now, let's have a look at what we call these. This is a maximum turning point because, looking like the top of a hill, when you're on top of it, you are at the highest point. So it's the maximum, and it's turning. Similarly, this is a minimum turning point because the apex is where the y value is at its minimum. These two are both called points of inflection. Now, we've already seen that points of inflection are places where the concavity changes. But these are special points of inflection that are also horizontal. Not all points of inflection are. But if you have a stationary or a horizontal point of inflection, and we use both those words to name them, then you've got it approaching from one side and then going up the other, and you actually have that flat spot in the middle. Now, to define what's happening here algebraically, if we look at what f of x is, now f of x is just the y value, isn't it? So it's how tall the graph is, up and down. Then we can say that for a small interval on either side of x equals a, so in other words, just locally around this point, all of the y values of the curve are lower than the y value at this point here. Now this point here, if we've got some value of x, we're just calling it a. So let's say we graph this thing on a Cartesian plane, and as we go along our x values, perhaps we're at 3 or 4 or whatever it is, we'll just call it a and say at that point, what's y? Well, we'd call that f of a, wouldn't we? Because we'd be subbing a into the function to see how tall, if you like, this y value is. So we'd say that all of the points on this curve here are lower than our high point. So f of x is lower or smaller than f of a for all of the points just in and around here. Now it's important we know that this is just locally, because this could be part of a curve that maybe has a high point but then goes up and has another high point later. So it might not be the highest point of the entire function, but it's a local high point. Similarly, here we've got a local low point or a local minimum turning point. So the values of f of x, which again means just the values of y, they're all higher along here than they are for this low point. So f of x is larger or equal to f of a in and around our point x equals a. Now what's happening here with these points of inflection is that the tangent to the curve actually crosses the curve. And you can see there that my line that's a tangent to the flat spot, it actually crosses over the curve itself in both cases. And the other thing that's happening in and around this point here, x equals a, is that the concavity is changing. So we go from being concave down to being concave up, or vice versa.